Okay, everybody. Welcome to today's webinar offered by both Scylla and Expero. A couple of items for upfront record keeping, housekeeping. Number one, there will be recordings sent out to everybody, all the attendees. The slides also will be provided. Lastly, all of the attendees should be joining by on mute, and there should be a mechanism for you to submit questions for a Q&A period at the end. Okay, so without any other delay, we're here to talk to you today about architecting a corporate compliance platform with Graph and NoSQL databases. So while today we're here to talk to you about compliance and entitlements, it is important to note that this mixture of technologies, JanusGraph and Scylla, are very appropriate and work well for several other use cases, not least of which anomaly and fraud detection, customer 360, Internet of Things use cases. But today we're here to talk to you about corporate compliance. So hello, my name is Brian Hall. I'm with Expero. I lead the graph and analytics practice here. Mahi?
Hi, I'm Mahidhar Kunturu. I'm a solutions architect here at ScyllaDB. I typically work with customers and help them achieve their business outcomes.
Okay, so a little bit about what we're going to talk about today. We're going to talk to you a little bit about what entitlements means, overview of the problem at hand, then we'll tell you a little bit about who we are at Expero and Scylla. I'll tell you a little bit about JanusGraph. Then we'll talk about why Janus and Scylla work well together. Then we'll talk about how we're modeling this entitlement problem differently and innovatively to solve some commonly complex problems. And then we'll go into a little demo and talk about performance, and then wrap it up with some Q&A. So what do we mean when we talk about entitlements? Usually what that means is you've got some notion of a resource, and in today's situations, we'll be talking about resources being accounts. And those accounts typically are accessed or somehow either accessed or revoked through applications. These applications are granted or revoked through parties, and those parties are somehow identified by logging in some identity. So how do we typically deal with this currently? What's the status quo? This model may be familiar to all of you, where you've got some notion either represented in Active Directory, LDAP, relational databases, where I've got groupings of people, right? I might have Alice, Bob, and Jane that are in accounting, and then Andy, Rick, and Sally are in HR. Suppose, for instance, I've got accounting. I want to allocate access to this certain account to accounting. Or for instance, maybe I want to decorate that and say everybody in accounting can access this account, but then also Sally in HR for some reason. Maybe I want to get a little more complex and I want to say only managers within accounting can access this account, but then Sally also still can, right? And then possibly I've got groupings of accounts. Suppose this account is not a simple checking account, but maybe a limited partnership. And maybe I've got accounting managers that can access one part of the account, and then Sally maybe can access the other parts of the account. And then possibly what I might have is subgroups within the account. Maybe my limited partnership also has corporate business accounts, and maybe I've only got the ability to access subsets of subsets. So in general, I'm sorry, I'm having trouble here. So in general, I've got an arbitrarily deep recursion, right? I've got accounts that may live within inside of accounts that may live within inside of accounts. At the same time, most companies have multiple layers of organizational structure where I might have analysts that report to managers that report to directors. I've also got VPs and C-level executives. So now that I've laid out the entitlement problem, who is Expero? In short, we're a consultancy, and we build products for complex use cases and expert users. Oftentimes, those require big data and graph data solutions, and we try to bring these ideas to reality. Oftentimes, when we come to engagements, we walk in with some tool sets and accelerators that allow us to extract business value quicker than normal, and we provide these in what we call finish-to-order toolkits. A lot of what we'll talk to you today is actually out on the JanusGraph.org website. I encourage you all to go out and read and peruse that at your leisure. So let's talk a little bit about the history of how we got to today. Starting back in 2009, the Apache Tinkerpot project was launched. That gave us the Gremlin query language, which is the lingua franca of graph queries to date. Titan was announced in late 2011, and it went to version 1.0 in 2014. There was a fork in 2016 of the Titan code base that launched JanusGraph in mid-2016. And as of 2017, JanusGraph was awarded the Bossy Award, which is awarded by InfoWorld, which is the best of open source software. That leads us to today. So the JanusGraph value proposition is that you've got up-to-date Apache Tinkerpot query support, keeping abreast of all the cutting-edge language constructs, all offered within the Apache Software Foundation license through the Linux Foundation and a vibrant open source community cultivating this code base. I pulled this list of users off of the JanusGraph.org website. This is just a short list of the people using JanusGraph in production right now. We happen to know and work with a few of these guys, and not only are they using JanusGraph in production, but they are using, some of them are using it on top of ScyllaDB, the solution that we're here to talk to you about today. A little bit about the nuts and bolts of how JanusGraph works. Key to the architectural design and decisions is a pluggable layer where JanusGraph sits on top of a pluggable storage layer. You see on the left many options, and Scylla being the notable one we're here to talk to you about today. At the same time, there's a pluggable layer for a full text and geospatial search, of which you could choose Elastic, Lucene, or Solr. So why would you want to use NoSQL for your graph backend? And the short answer is for horizontal scalability and fault tolerance, right? You no longer have single points of failure. You do not do joins, and you can go as horizontally scalable as necessary, allowing you for all kinds of data volumes, terabytes, even petabytes. So why would we want to go with JanusGraph and Scylla? Mahi?
Yeah, today I'm going to go over some basic design principles of Scylla and also present you with some results when you run JanusGraph with different NoSQL backends. ScyllaDB is a NoSQL database which is extremely performant, highly scalable, accommodates flexible data modeling, and overall resource efficient. For those of you who are new to ScyllaDB, we are a drop-in replacement of Cassandra and remain API compatible with the Cassandra client ecosystem. Cassandra is really known for its high availability and scalability, but it has a few design flaws which often result in highly inefficient deployments. We cherry-picked the best features from Cassandra and added a lot of enhancements to it. We offer open source, enterprise, and cloud versions of our software. And our founders, who were the creators of the KVM hypervisor, with very deep Linux kernel experience, have come up with this product. And also you would see on the right side a few of our name brand customers. Next slide, please. So these are some design principles that differentiate Scylla from other NoSQL databases. I will expand on them in the next few slides. Next slide. To begin with, we rewrote Cassandra and C++ to efficiently use the underlying hardware. This results in faster performance and lower latencies. So you get the benefit of the modern architecture and design of Cassandra without the inefficiencies of the JVM. The client side of the Cassandra ecosystem absolutely works with the Scylla server without any code changes. There's also a misconception that all of Scylla's performance comes because of the fact that it is written natively. Maybe 10% of the difference between Scylla and Cassandra's performance comes from this fact. I'll explain about the other design principles in the following slides. Next slide. Next slide. One of the unique features of Scylla is its shard per core isolated architecture, where each Scylla shard is associated with a core. This guarantees that the system is never starved of compute resources, versus the JVM model, which is depicted by the picture on the left, where compute resources that are shared and interleaved among various JVM threads. Basically, this introduces a lot of inefficiencies. And as you see from the picture on the right, Scylla is a shared nothing architecture. We take this architecture also a notch higher by providing the necessary RAM per core as well, which is used by the mem tables, and they're isolated by shard as well. So you're never starved of either memory or compute resources. Next slide, please. Underlying Scylla is a framework called C-star, which is thread per core asynchronous I/O framework. A C-star task is scheduled and the core, and it has the core until it finishes the processor bound computation. Being thread per core means whenever anything on the core blocks or sleeps, like I/O wait, there's nothing to be scheduled in its place on that core. This is the main reason we prefer and insist on running XFS, so we get the performance benefits of using an asynchronous file system. But the fundamental point is there are no locks in our system. Next slide, please. So the next key design choice we made was simplifying the cache. Cassandra has caching, but it's quite complex to tune. There's key caching, row caching, Linux caching, on-heap caching, off-heap caching. Basically, this results in an enormous amount of tuning. And if there are any changes to the data model or throughput of your data, oftentimes you need to completely retune the caching layer, or else you start suffering latency problems. We make this a lot simpler. Scylla built its own caches, which are highly optimized and tuned to your workload. By default, we take a fixed amount of RAM that's available and use 50% of that for storing mem tables and the other 50% for caching. Row caching and key caching are tuned and available by default, which overall aids the performance of the system. We even disable Linux page caches, which is essentially a blocking entity with very poor control over latencies. So we directly write it to Scylla's cache. So you get the benefit of the faster performance with pretty much zero tuning out of the box. Next slide, please. The next design decision I will expand upon is our I/O scheduler. Both Cassandra and Scylla are disk-based systems. We do use RAM as best as we can, and we prefer NVMe disks. And also disks are much more cheaper than RAM. So with Cassandra, when there is a sudden burst of writes, the JVM simply passes them on to the disk controller, which in turn queues them up using the disk buffers. The challenge with that is there's no prioritization of these I/O requests. So if one request is for compaction and the next request comes in for a read, then the read is going to get stuck behind the compaction. So how do we do this differently? When we install Scylla, we benchmark the hardware that is provided. And there's a graph on the left side of your screen which shows how a typical benchmark would look like. So we create a number of concurrent requests and figure out what is the max throughput we can achieve before the disk starts buffering. We try to find so basically we're trying to find out what is the max concurrency that can be supported from the disk I/O standpoint, and before we take on any latencies. So when we get a big spike of writes, we will queue them, but we're going to queue them intelligently, where we're going to be able to prioritize the queue and maintain the read and write latencies, which keep the system nice and stable with low latency. This way, the C-star framework underneath has a predictable way to prioritize things like commit log, mem tables, and queries over compactions and repairs and other maintenance activities. Next slide, please. The next design choice we're going to touch upon is self-optimizing. Scylla is an autonomous database, which means your admins get the benefit of minimum tuning. As we discussed when we installed, Scylla is going to tune itself and benchmark the proper disk and RAM and CPU provided, and the network as well. There are essentially all the different backend operations which it needs to handle, which are commit log, mem table, compactions, queries, and repairs. These individual operations are scheduled through the C-star scheduler. So basically, we move scheduling out of the kernel space into the user space, where every request is parallelized and given its own priority. When a request for a CPU resource comes in, we do our own prioritization of that request based on the workload at that point, and then use our own scheduling to schedule the task. Next slide, please.
Sorry, go ahead.
So using all the design principles, that's where you start seeing the differences. And here is one of a benchmark from our customer IBM Compose team, which presented in our user conference recently. So during this multi-phase workload, they first inserted around 40 million vertices, and then in the next phase, as shown in this graph, insert about 30 million edges with one property for each edge. This workload is a mixture of both reads as well as writes. And while testing on this workload, Scylla offered the highest throughput. As shown in the graph, it's about 132K edges per second compared to Edgebase or Cassandra, which were about 50,000 and 30,000 respectively. Scylla outperformed the other two in terms of CPU utilization as well, where it was able to achieve 90% CPU utilization. So you're able to get the most out of the hardware that is provided for running your backend database as well. So I'm going to be providing links to this benchmark and a detailed talk to from this customer in our conference, and the links as follow up. So I'll give things over to Brian now, and he's going to talk about how to model entitlements in a different way using Janus and Scylla as the backend.
Okay, thanks, Mahi. Okay, so where we left off is a problem of arbitrarily deep recursion on two layers, right? I've got accounts within accounts within accounts, and then I've got organizational hierarchy that can be arbitrarily deep, and I may actually have matrix reporting structures as well. So let's talk a little bit about what it means to store things in a graph. I've got essentially two different notions. I've got nodes, are commonly called vertices, and edges, which denote relationships between the two vertices. For instance, in a healthcare situation, I might have patients that receive care from a doctor, or maybe a doctor provides care to patients. I've got this notion of a degree where I might have numbers of edges coming into my vertex or numbers of edges going out from my vertex. In addition to that, I can have self-referring vertices where I actually refer to myself. We talk about the types of edges. I can say A is directed to B in some fashion. They also can be undirected, where implicit the direction does not matter. Moreover, what I can also do is hang attributes off of vertices and edges, right? In this instance, maybe Alice can access this account, but she can only access it in read-only fashion. So now let's go back to our original problem where we're trying to model these entitlements within a graph, right? So here we've got this notion. This is a schema that we've got in our JanusGraph schema viewer, and I've got what I've modeled here, resources, and in our vernacular, all of our accounts are resources. We've also got this self-referring edge where resources can be children of other resources, where that handles my arbitrarily deep nested account groups. I've got this notion of profiles, like accounting has accounting has access to this certain account group, identified by profiles. And then I've got to log in, and that's a key point. At the time of login, I've got to identify, who am I? I am Brian, and I am an accountant. And that tells me that I have access to certain profiles. And then lastly, I've got my organizational hierarchy, where I might be identified by a certain group, and then I have some management structure where I can have direct reports, or I can be managed by, and that's represented in my party. So I've now got, with these self-referring edges, I've got both of my arbitrarily deep recursive relationships modeled. So if I wanted to walk through the code for a couple of common use cases, right? So for instance, can a certain identity access a particular account, right? So and for those of you unfamiliar with Gremlin, this is just a simple Gremlin query. I can given a certain identity ID, and this would be given to me by somebody logging in, I can then decide this identity has access to some profile. I've assigned my identity as that I'm in accounting, or I'm an accounting manager, or whatever. And then I also can represent the relationships of resources or accounts that I can have access to, right? So if this comes back with a result set, then I have access to the account. If it does not come back with resources, then I do not have access to that account. At the same time, I might be able to say something, another common use case might be where I might want to say something is going on with this account, who possibly could have accessed it, right? So I can start from the other direction, looking for resources, a particular resource, and then walk the graph backwards such that I can say, okay, this account can be accessed by accounting managers and somebody in HR, and I can walk back to the identities and the logins of who possibly could be accessing this account. Oops. Sorry. So anyway, let's talk a little bit about demoing some of the code here, and just by way of setting up what I'm about to show you, we took a sample data set, and we loaded up a company with roughly 100,000 employees and on the order of about 5 million account resources. And then we put this into a 3-node Janus cluster alongside or backed by a 3-node Scylla cluster. So what I'm about to show you is hitting that. And in the interest of measured twice and cut once, I will confess that I recorded this demo this morning just to make sure that Murphy's Law did not bite me too badly. So let me just walk you through what some sample uses. Okay, so let's take a look at our entitlements viewer here in the admin console. Starting out here, you see the graph schema that we just walked through: party, resource, profile, and identity. You also see here that we can manage indexes from inside of here, and it's good to note that just like you can in good relational database modeling, you can create indices for a quick lookup on properties on vertices and edges. And then let's go and assume that we want to look up the list of resources or accounts that a particular person might want to have access to. And here I've got the mechanism, the ability for us to look at the results of that query. That's a common Gremlin query that we might pose. And here I've shown a very, very complicated a graph model here with somebody who's got access to several accounts. Right here you see 268 vertices and 280 edges, and you see how snappy that thing came back. So this is your admin tool and a mechanism with which you could actually see things from an administrator perspective. Typically, you probably wouldn't want to use that perspective. So let's see how this might look in terms of an end user application. Here, what we've got is an entitlement viewing application that perhaps a network administrator of some sort might want to be curious, might want to use for investigation. Here, maybe I might want to be looking up somebody in particular. In this case, we've got, we're curious about this person, Fran Farmington. We see in this identity, we've got something going on here. We see an alert here. Maybe I want to drill in. And now I see, here's Fran. There's something going on here with Fran, somebody that she manages, and something going on with accounts. Maybe I want to drill into the accounts, and I can see that Fran has access to several things. She's got project planning, ERP, HR, some time tracking and accounting, and she's got access to this thing called the Innovation Hub. Right, so maybe something's going on here with that Innovation Hub and somebody that she manages, right? So maybe I want to drill into the people that she manages, and I see doesn't seem to be much going on Maggie, but over here I see that Dennis, the other person that Fran manages, was placed on administrative probation for some reason. So maybe we want to delve in and see what's going on there, right? So maybe I see that Dennis has got some sort of issue going on to accessing the Innovation Hub, and perhaps I want to see what's going on with respect to this timeline, right? So Dennis has been trying to access this Innovation Hub from external devices, right around the time he was put on administrative leave. So maybe that's something that warrants some further investigation. So this is just one simple use case with which this entitlement viewer and entitlement model can be used for your corporate purposes. Okay, there we go. So let me go back to my slide deck. So anyway, I hope that gave you a little taste of how this sort of infrastructure might be used, and a little day in the life from a user's perspective. If I were to talk a little bit about how did this thing perform, so even with this small cluster, we took it and we stressed it to give it a little bit of a load and try to see how it performed. And we were able, even with this small 3 by 3 Scylla and Janus cluster, we were able to support on the order of tens of thousands concurrent users with even the 99th percentile, the P99, well under 200 milliseconds. The P95 is 23 milliseconds. And in full disclosure, while the bulk of the time is spent at the Janus layer, we were having trouble. We were having trouble actually getting the Scylla cluster to break a sweat. So hopefully that gives you a little sense of what we're proposing here and what we're talking about. I think I will now turn it over to some Q&A. Like I said earlier, I believe there's a facility for the attendees to drop questions into the webinar. I will start with one asking about other use cases. So what other use cases are applicable for this kind of technology? I'll happen to tell you I know that I know for a fact, because we're actually doing it with another client, a lot of cybersecurity, anomaly detection type use cases. Those are being done currently right now. Other ideas are in the order of IoT. I've got sensors on machinery streaming in at very high rates, and I want to be able to capture them on the way in and determine shapes of behaviors. That's another very common use case that we see. We see anomaly detection with respect to credit card fraud, those sorts of things. These are other use cases that we see quite commonly. And then last but not least, one classically graphy use case problem that we see is around supply chain, where I might want to I've got a disruption with a supplier, and if I can't buy my bolts, my nuts and bolts from this one supplier because he just got acquired by my competitor, what are the things that are not going to make it to the shelf at the end of the month, right? So that's the sort of thing. That's the sort of thing that we actually see very, very frequently. So that's one use case, or a handful of use cases that we've seen. Let's see. In terms of the entitlement tool, I think we covered what the back end is, right? So another question out there is, what is the entitlement tool built in? So what we've got on the back end, as we've covered, certainly Scylla as the storage layer, and Scylla is the storage layer with Janus sitting on top. The front end tool we have here is a web application built with a suite of, like I said, tools and accelerators that we have put together here at Expero, and those tend to run in JavaScript React, coupled with some REST and GraphQL endpoints, typically provided through Node.js. We can talk to you a little bit further about the front end visualization tool that we commonly provide with our projects. With respect to, let's see. How much would all this cost? I don't know, Mahi, if you want to talk about any of the Scylla costs. I can tell you that what I showed you today, well, JanusGraph is open source, so there's no cost to that. Typically, our projects can be completed certainly to get going in the $50,000 to $100,000 range. Mahi, I don't know if you want to talk about your anything with respect to that.
Sure. Yeah, I mean, Scylla is offered in 3 variants. There's an open source version of ours, which is free to download and use. There's an enterprise version of ours as well. For the demo that we did, it would be around 10,000, I think, based on the instances. I think we used i3 2XLs. So all things included for our enterprise version. For our cloud version, there's a little bit of a maintenance on top of it. I would typically use our TCO calculator, which we have on our cloud portal. For if you're open to exploring exactly what we saw in the demo using Scylla Cloud.
Yep. Okay, so let's see, a couple other questions. Certainly around tuning JanusGraph. And I will tell you that there's one question out here. Trying to use JanusGraph in a query-like tree, we're having trouble getting it to perform. Yes, there are ways to make it perform better. Usually what we tell customers is make sure that your query patterns align with your model. If you're trying to do for those of you SQL people out there, if you're trying to do a 12-table outer join and none of the columns are indexed, you're going to have poor performance. So we typically tell people that you need to make sure that your query patterns and the way you intend to use your graph need to align with how you've modeled it and how you've constructed your schema. How do we compare with AWS Neptune? There are a handful of things we typically advise customers on that. Cost is one, obviously. Cloud provider versatility is another one. Whether or not you are eager to embrace Gremlin versus Sparkle, which is a different query language. Neptune supports. Those are many of the things that we would advise people to consider. And then in terms, let's see. Mahi, there's one out here about Janus, part of the Scylla Cloud. I don't know if you want to take that one.
So Janus is that you would have to install Janus yourself on an instance, preferably on AWS or any cloud you would prefer, and then you can for the Scylla portion of it, which would be the backend to JanusGraph, you would simply change the IP addresses to point it to the Scylla instance running in Scylla Cloud.
Mm-hmm.
And it should be able to automatically pick it up from there.
Yep. Yep. And then last but not least, largest deployments in terms of data. I think there are, that's answerable in many ways. We typically see there's no simple answer to that. We have seen projects and been part of projects where the number of nodes and edges are in the billions. What I would tell you is again to make sure you model your problem consistent with how you intend to store it or and query it. Right. Oftentimes, if you're familiar with Scylla and Cassandra and even HBase for that matter, backends, you tend to have many projections of data in such a way that you want it to come back, right? So the laws of physics have not been repealed. Good data modeling and good query patterns still apply. So let's see. I think
there was one more question regarding comparison with Cassandra as the backend, also how it would be handled, with Neo4j versus Janus.
Let's see. So let's see how many. So that one is actually in a way, having a shared nothing backend that's built from the ground up to be horizontally scalable. Neo handles clustering in a much different way. I would argue that that going highly horizontal with Neo4j tends to be problematic.
Yeah. And if I can add, Scylla is something which both scales up as well as scales out. With Neo4j, you get only scale up. It is not a distributed system. Obviously, it is one of very good graph databases, but if you want to have the performance benefit of having scale out as well as scale up, because Janus, on the other hand, does both is very good at scale out. Mm-hmm. So you might want to use a system in the backend which scales out as well and can match through the throughput that your Janus graph instance needs. So I think there is a much more synchronous ecosystem there with Janus and Scylla.
Yep. Okay. Another one just came in about not necessarily just OLTP use cases. You can, as part, we see very, very frequently clients using Spark and other analytics engines to run jobs against the JanusGraph instance. That's a very common use case. So pre-computing values, running analytics jobs in order to find anomalies in your graph. Sometimes those are OLAP type jobs. Sometimes we might want to decorate my graph with attributes that may be inferred by the shape of the graph, right? So if I want to compute, the similarity or other shape of the graph in its entirety, I might want to run OLAP jobs before I actually do the writes across the entire graph. So those are the sorts of things that we see in terms of OLAP and oftentimes using Spark.
I mean, if I can add, through Spark, you would still have to query through Janus. There is the data which gets written into Scylla is of a custom encrypted format, which only Janus would be able to access. And the data model as well, which gets created in Scylla, is completely automated by Janus. So that is another fantastic benefit you get when you run Janus and Scylla together, where Janus automatically creates the necessary schemas in Scylla. But there is this limitation where if your Spark instance is trying to read directly from Scylla, you would still have to go through Janus to be able to read the data which is stored in Scylla.
Sure, sure. I should have been more clear. The you know, I may want to run a big complex gremlin queries in my OLAP engine, and that's very, very commonly done in Spark, yes. I believe that's all of the questions I see in here. Well, like I said, the recording and the slides will be going out to all the attendees. Do you have anything else you wanted to add, Mahi?
Yeah, I think there was another question about Scylla Cloud. I did give some links which the users can get started with. You know, these days things are working in, you know, the new thing is to try everything in a hybrid fashion. So in a hybrid cloud is very, very much what most companies are trying to do and scale. So yeah, we do provide Scylla Cloud on AWS for now. And we are going to be providing in other clouds as well, including Google Cloud and Azure. It is there in our roadmap, and if anybody has a specific request, please do reach out. You can either reach out to me directly or through our public Slack as well, and we would, you know, we would be happy to work with you on any of these requests that you have, and make sure to align accordingly.
Okay. I think that is everything I see here in the Q&A. Thank you, everybody, for your attendance and your attention. And with that, I will bring this to conclusion.
Thanks a lot.